Welcome to Quantum Computing Essentials Part 1, Lecture 5. Today, we'll be discussing on certain topics, which are very fundamental. The topics are the matrix norms, which will be very similar to vector norms with certain more protocols. Then we'll be talking about the inner product space, which we missed in the previous lectures. Inner product space. Inner product space. And also we'll be talking about the set of orthonormal vectors and orthogonal vectors. So writing in short as orthogonal vectors. Orthogonal vectors. So these are the topics for today. So the first part is the matrix norm. These are very important because when you'll be trying to design certain algorithms, so you'll come across different kind of QoS parameters, quality of service parameters, such as example, the fidelity, mean square error. They are basically you have to define certain distance functions, and you will come across several norms. Maybe it is a vector norm. If it is a vector minimization problem, if it is a matrix minimization problem, you can have a matrix norm problem. So we'll be trying to cover some of the important matrix norm. So what is a matrix? So I will have formal definitions. Before that, there is a rule that if you have a matrix A and B, if they are say compatible matrix, if the matrix multiplication is possible, so they are not necessarily equals to B into A. Okay, multiplication of B into A. For vectors, they may be same, but for matrices, they may be very different. So matrix multiplications distinguishes matrix spaces from the more general vector spaces. This property is quite different. Okay, so for which we have the CBS inequality, that is the CBS inequality. So what is CBS? Cauchy, the Cauchy-Schwarz CBS. Please excuse if there is any spelling error. So CBS inequality, or in short, CS inequality, Cauchy-Schwarz inequality for the matrix spaces. So if you have a matrix A, earlier you have seen for the vectors cases, some inequalities like triangular inequality or the product inequality. So now you see, if you have a product like A is a matrix, X is certain vector, so I represent that Ket X. Okay, and if you have the two norm of this whole, so it should be lesser equals to the A norm, Frobenius norm of A, product with this Ket of X, two norm. So which can be extended for two compatible or conformable matrices A and B. So here you have the vector X and the matrix A. Now if you have two matrices A and B, and there is the Frobenius norm, then it will be lesser equals to the Frobenius norm of A product with Frobenius norm of B. Okay, so it also indicates the sub multiplicative property. So it indicates this too for other norms. If A and B with some general norm of 2 norm, then also it satisfies this. This is A into this is B. Okay. We'll discuss more about this Frobenius norm, what is this and all these things. So this is one important fact here for the vector norm. This is called CBS inequality. Okay. This is a very important inequality. So I request to keep a note on this. Okay. This is called CBS inequality. Okay. So the general matrix norm. So let us define it little formally. So a matrix norm is a functional map this is very important. It's a functional map. So basically we'll come across in the functional analysis. This is very useful. So a matrix norm is a functional map from so either a complex m cross n with m number of rows and n columns to real number r. This is important to note. Okay, norm is here real. Okay, even if it is a map from the complex m cross n dimension to r, or it may be a matrix with real elements of dimension m cross n to the real line. Okay, so you may have a matrix with complex entries, but your final norm or the matrix norm will be a real quantity. Okay, non-negative real quantity. And it should satisfy. So it's a functional map from this to this or this to this, and should satisfy certain properties. So some properties they have to satisfy. So what are these properties? The first property is that the representation is like this. So norm of A, it's a general norm basically. Okay, it can be 2 norm or Frobenius norm or some other norm. So whatever norm it is, so it's a general representation. The norm of A, it should be a non-negative quantity. That means greater equals to 0. Okay, and if it is 0, so if the norm is 0, if the norm of A is 0, then the matrix A should be a 0 matrix. Okay, it's a 0 matrix of the same dimension. So this 0 is basically dimension of 1 cross 1. It's a scalar. Okay, it's a scalar, means it's a 1 cross 1, and here basically it's a matrix of the same dimension of A. If A is your m cross n, then this will be another m cross n. Okay? But it's this should belongs to R. Okay, and this should belongs to R m cross n of all 0 elements. So this is the first property. It should be non-negative. This property is non-negativity. Okay. Non-negative property. Then the second property. So the question is why I am covering all these things, because we will be dealing with quantum state, the observables. We will have a product, whether the resultant quantum state is a valid quantum state or not. That should obey these vectors, norm properties, as well as the probability postulates. Okay. So we'll recover all these things with examples later on. So the second property is the a constant multiplied with a matrix, their overall norm should be the modulus of this constant multiplied with the norm of A. For all constant belongs to the scalar field F. They may be complex or real quantity. So the field F, okay, this may be a complex field or a real field. For all such alpha, it should satisfy this particular property. This is called scalar multiplication property with norm preserve. So the third property of this matrix norm should be, if we have a matrix A, another matrix B, and if we take their addition and then we take the norm, then it should be lesser than equals to norm of A, same as our triangular inequality for the vectors, okay, plus norm of B. Okay, for all such A belongs to your M cross N and B should be of M cross N. That means the dimension should match. Okay, if A belongs to Rm cross N, so also your B should also belongs to the same dimension, Rm cross N. Okay, they should be compatible. Okay, now so if you have the product A and B matrix multiplied A and B, then their norm should be less than equals to norm of A multiplied with norm of B. Okay, so for all A and B conformable, A and B should be conformable. That means this product should exist. Okay? Conformable. Conformable. So this is the submultiplicative property. Okay. If all these properties, all such four properties that I have mentioned, this particular properties, property number 1, 2, 3, and 4, then we say that it's a valid norm of A. Okay. So let us discuss a little more about this thing. The Frobenius norm. So what is this Frobenius norm? Is that it's a very important norm which is given only for the matrices and not for the vectors. Okay, so what is this Frobenius norm? Frobenius norm. What is this? So say for example, take an example first, then we'll define it formally. Suppose we have a vector space C M cross N. Okay, is a vector space of dimension, say it's a vector space of dimension M into N, say. Okay, so using this, so some matrix we take which belongs to this particular vector space M cross N can also be measured can be measured uh, can be measured in CMN because it's a vector space. So for example, take A as a matrix first. So we have 2, -1, -4, and 2. And we define a norm like this. Frobenius norm of A as the square of all elements, the addition of square of all elements. So 2 square minus 1 square plus the -4 square plus 2 square. And if you take the square root of all this whole thing, whole stuff, okay, so you will get an answer. And that particular answer says it is the Frobenius norm of A. So if you take the individual element square and take the sum, and then the overall square root will give you the Frobenius norm. Okay, so this is the simplest notion of matrix norm. So it's the simplest notion of matrix norm. Simplest notion of matrix norm, and it is known as the Frobenius norm. It is known as Frobenius norm. It has another name, which is called the Hilbert Schmidt norm. It has another name, also known as the Schur norm. Okay, so they are the different names for this. Now, so we can formalize the definition as below. So if you have a matrix A, the Frobenius norm you can write as the summation of all Aij. Aij are the elements of the matrix. You take its square, okay, over all elements Ij. Okay, so what you get the Frobenius norm square, right? If you, because you are taking the square this side, so it will be square again. Okay, so note that it will be actually, if you multiply this matrix with this matrix and take the trace, that means if you multiply A stars, its transposition or conjugate transposition, and the matrix A, and take the trace of this particular thing, you will get the same answer. Okay, so this property can be useful for all such for all A belongs to some real or complex M cross N. So what this property is saying is that, so the earlier example you can check. So in the previous example, here you can see this particular thing. So this is A, okay. So if you take A star, okay, so what is A star? A star will be its transposition. So it will be your first thing will be 2, this side will be -1, this side will be -4, this side will be 2, right? So now if you multiply this two matrices, okay, then if you take the sum, okay, so basically after multiplication, the first element will be how much? 2 into 2 will be 4, okay. The last element will be coming possibly 1 because their trace will be 4 plus 1 will be 5, okay. So check the last element, okay. So if how to get this last element of this a star here. Okay, so let us multiply. So 2 into 2 is your 4, and this you have to multiply with this. So 4 plus 1, 5, right? So you are getting this as 5. This side with this side. Okay? So 2 into 2 is 4. -1 into -1 is 1. So 4 plus 1 is 5. Then you have to multiply this with this vector. So 2 into -4 is -8. Okay. And if this is your -8, and this -1 with this 2 is -2. So -8 with -2, right? So it will be -10 this side. Then you have to multiply this with this, and the last element will be how much? -4 into -4. So I'm doing the last element. There will be some element. So -4 into -4 will be 16. Okay. And then if it is 16, and this 2 will be multiplied with this 2, it will be 2 plus 2 is 4. Okay. So how much it is? 16 plus 4 is 20 plus 5. So answer is coming as 25, which is actually the square of this, right? 5 square equals to 25. Right, because you have to take the trace of this, means this element plus this element sum. So it will give you the Frobenius norm square. So Frobenius norm will be square root of 25. It will be 5. Okay. So this is one very important property for this. So now um, let us define some more norms, okay, for the matrix. And that is we call as induced matrix norm. Okay. The induced matrix norm. So a vector norm that is defined on CP. So how I am defining is that uh, a vector norm that is defined on the dimension CP for some P may be equals to M or N, the number of rows or the columns. It induces a matrix norm. Induces a matrix norm induces a matrix norm on the dimension on C M cross N. Sorry for this. M cross N by setting as A, the norm of A, equals to the max of the product Ax, its norm, for all x whose norm equals to 1. Or you can simply write it as max of A into ket x, because the ket x will have norm 1. So using this quantum notation for the state vector, this it will be the norm of it. Okay. So for all A belonging to the dimension C complex M cross N, or and this ket x, the vector x will belong to C N cross N. So hence induced matrix norm is compatible with its underlying vector norm. Okay, so that we already have shown. So let us see some geometry in this particular part. So there is another definition. So A is called non-singular. A is called non-singular if minimum of this, if the minimum of the norm A into ket x, if the minimum of this norm is equals to 1 by norm of A inverse. Okay. So if it is a non-singular, then this is the case. Okay. So so if you have a unit sphere, how will be the geometry? Let us see. Suppose you have a sphere like this. Sorry for such a bad drawings. So this is a sphere for the simplicity, and so if we stretch, okay, so it can become an ellipse like this. So this side will be the plane for the major axis. This is the major axis of the ellipse, and there will be the minor axis of the ellipse as well. Okay. So this particular side, the distance of this, or the value of this particular, or the amplitude of this particular line will be stretched by the norm of A. Okay, which is defined as the maximum of A into ket x for the vector ket x equals to 1. So this is the length of the at most sphere you can stretch. So the length will be the norm of A. Okay, and this minor axis. Okay, so it will be 1 by norm of A inverse. So the minimum of this particular minor axis will be, length of this minor axis will be 1 upon A inverse norm. Okay. So this is one important thing to note. Then we'll have the matrix 2 norm. Okay. So some more facts I'll be giving here. So likewise, vectors will have different matrix norm, like 2 norm, the Euclidean norm earlier, as we have seen, right? But there I'll be giving certain facts other than the definitions. So the matrix 2 norms. Okay. So basically the matrix norm induced by Euclidean norm is a matrix 2 norm, and it is represented as the 2 norm of A defined as, so I'm using the Ket notation. So by default I'm taking that Ket of x, the norm of this, okay, norm of the Ket of x equals to 1 is our assumption through this particular part, matrix 2 norms part. So the 2 norm of A will be max of this a Ktex 2, okay, because Ktex this norm of Ktex will be 1. So this is defined as the 2 norm for the matrix A, okay, and the fact is that it is actually equals to the square root of lambda max, where lambda max is the maximum, lambda max is the maximum eigenvalue of this particular matrix A. So I'm writing as this max of lambda A. If lambda of A is the spectrum, okay, what is the spectrum? The spectrum is the set of eigenvalues of a matrix, okay, represented as lambda of A, which is actually the set lambda 1 comma up to say lambda n, if there are n eigenvalues of this particular matrix A. It can be different numbers depending on these conditions of A. So the highest element is the lambda max of this particular set, and if you take the square root, okay, you can have the 2 norm of this matrix. Then some more facts. So if A is non-singular again, okay, so the A inverse 2 norm of the A inverse matrix inverse, it will be the 1 by square root of lambda minimum eigenvalue of this particular matrix, where lambda mean is the minimum of the spectrum lambda of A. So lambda max and lambda mean are the largest and smallest eigenvalues, okay. So the matrix 1 norm and matrix infinity norm. So let us discuss a little bit about this. The matrix 1 norm, 1 norm of a matrix. So written as the norm of A1 is defined as the max of 1 norm of A into Ktex, okay, Ktex is actually have the norm 1. So it is actually the maximum of summation over I max over J, where I is the rows variable that goes through rows, and this goes through the column J. Then it is the sum over basically I. A, I, J are the elements. If we take just modulus or 1 norm, and it is actually, the fact is it is actually the largest absolute column sum, largest absolute column sum, absolute column sum. In short, I'm writing call uppercase n column, absolute column sum. Now So what does it mean? Basically, you have the matrix, you have multiple columns. So you take the absolute sum of each column, and among all such columns, okay, the maximum absolute value will give you the one number. So then you have this infinity norm, okay, of a matrix represented as A infinity and defined as similarly. So here I am explicitly defining it as the max of Ax. Instead, ktex I'm writing as x is a vector such that the infinity norm of this vector is 1, and we take the infinity norm of this whole stuff, and it will actually give us the reverse of this first problem, that is the max over I and summation over j and modulus of aij, which is actually the largest absolute row sum. Okay, so typically for a matrix, this norm is also known as the Saturn norm, Saturn p norm of A. And sometimes if you have if you have a matrix with p norm, so if p equals to 1, sometimes we call it as a Saturn p norm or the nuclear norm. Okay, nuclear norm, sometimes we say it as a nuclear norm. And if p is 2, sometimes this 2 norm of a matrix, we call it as a spectral norm. Okay, spectral norm. Okay, so spectral norm is largest for A, P positive semi-definite. If A is negative definite, this 2 norm is not necessarily the largest norm. Okay. So this is just a fact to note. So this is some facts about this particularly known as this matrix norm. So now we'll go for the inner product spaces. So I suggest you all to compare what are the vector norms and the matrix norms and compare them. Okay, so and take certain examples and practice on some simulation platform like MATLAB. Inner product spaces. So basically, they are some special vector space. I'm calling it a special because they possess some additional properties on the vector space. So sometimes, so just loosely speaking, they are sometimes known as the coordinate. Sometimes they are called coordinate independent or coordinate free spaces. So they sometimes are coordinate free. So if you want to define something irrespective of coordinates, so sometimes we come across these terms, the inner product space. So little formally, so we can define it as an inner product space so these are very important to understand the Hilbert spaces. A complete inner product space, basically a Banach space, is a Hilbert space. So this is very important. Inner product space. Inner products. So an inner product on a vector space, on a vector space, An inner product on a vector space V is a functional mapping. Is a functional mapping uh, of ordered paired of ordered pair of vectors So I'm taking as a kx and ky. You can take this kx and ky, say they are some arbitrary vectors, not necessarily quantum state, because for quantum state the norm should be one. So they are some arbitrary vectors, kx and ky, and they belongs to the dimension, say Rn. Okay, so it's a mapping of this to a real or complex, to a real and or complex. This is very important, or complex. So in case of the norm, definition norm, we come across the thing only real. But here actually you come across it can be real or a complex quantity. Okay, so typically it's a real or complex scalar. And represented as the kx comma ket y. So we have taken the ket y, right? Like this. So in simplicity, we write it as this. Simply we write as kx comma y. Okay. Other things are assumed such that this properties hold. Such that there are certain properties. Such that it satisfies. So some properties are there. The first of all, again, kind of while we defining the norms, the similar kind of things will come here. So the inner product of x with x, okay, will be always greater equals to 0, non-negative, and it will be 0 if the inner product of x and x is 0. Then there should be an obvious that x is actually 0 vector, that x get x is a 0 vector. So then only this is possible, otherwise it's a non-negative quantity. Second property is, if you take the inner product of a vector x together with alpha into y, some scalar alpha is multiplied with y, it should give the result alpha into the inner product of x and y. Okay. For any scalar belongs to the scalar field f. It can be a complex, it can be a real number. Then we have the ktex, some vector. So with some another two vectors y plus z. Sometimes this kind of notations are also written as this fashion. Okay, this notation and this notation, so they are equivalent in this case. So the result will be again the inner product of x and y plus y and z, inner product of y and z, y and z. So for all x and y belongs to Cn. Okay? For all ktex and Ky belongs to Cn or Rn. Okay. So whether we are taking complex vectors or scalar vectors like this. So we also write it as this. So for two vectors, Kx and Ky, the notation this x comma y, we write it as basically the transposition of x into y. Okay. So this is a standard thing where x and y are vectors. Okay. So again, we can write it as like this. Inner product of x and y. This is a Dirac notation. So it's typically it is so it's like this. So this is basically x transpose is written like this into this k to y, right? So if you multiply this with this, okay, so you can assume like this. So it's so basically again there is the error is basically here. So it is you have to take the transpose of this, okay. Vector of x, its transpose, then y. Okay. So it will be basically like this into this. So in short, it is written as this. The same thing will come again. Okay. So this is the inner product, which should be non-singular, known as the so the inner product of x and y. So if you have two matrices, say A and B, you have two matrices A and B. So you can write it as the inner product of A and B like this. And an important fact is that it is basically equals to the trace of the A star into B. A star means conjugation of A product with B, provided they are basically conformable, means the product should exist for all A and B belongs to C M cross M. C M cross M, right? So so this is one thing. And sometimes for the continuous valued function, we can again define this kind of vector space as, so if you have the so this is for the matrix. Then if you have some V is a vector space, is a vector space of some real valued continuous, some real valued continuous, real valued continuous function on uh, on some A comma B interval, then the inner product of some functions f with another functions g will give you the result as the integration of A to B. The function, say f is a function of t, real valued function, ft into gt into dt. So this is the inner product for the two functions, continuous valued functions ft and gt. Okay. Then again we come to the inequality. Okay. These kind of inequalities are very frequent in quantum literature. So again, we come across the general CBS inequality. Okay, Cauchy-Schwarz inequality. So I'm calling it as a general. Okay, the general CBS inequality for the inner product inequality So we have seen it for vectors and matrices, matrix and matrices, and now for the inner product. So if you have two vectors x and y, okay, and you take their inner product, then it should be lesser equals to the ktex, the norm of x, the vector x, and product with the norm of y for all x and y belongs to the vector space, say V. Okay, so this is the relation. Okay, and there is a modulus. So this is the relation between the inner product space and norm given by the CVS inequality. Okay, so it equally holds if you have some y equals to alpha x, alpha belongs to some complex numbers. So you can compute the alpha at the inner product of x and y divided by x squared. Okay. So so there are some other norms like elliptical norms and those things. So they are very easy. I'm not covering those things. So now let us define some orthogonal vectors. So you can follow some other norms and definitions from standard books that I have mentioned in lecture 1. So now I'll cover the orthogonal vectors. Okay, so in an inner product space V, okay, in an inner product space, in an inner product space, inner product space V, if you have two vectors, say you have two vectors, some kx and ky, they are some vectors, and they are said to be orthogonal. They are said to be orthogonal. They are said to be orthogonal. That is, kx is perpendicular to the ky. If it satisfies that the inner product of x and y is 0. Okay. That means x transpose the vector y, it equals to 0. For all such vectors x and y, we'll call that these vectors x and y are they are orthogonal vectors. Okay. So this is one part. Now so suppose we have some set of vectors. Okay, say there is a set gamma, and there are certain vectors u1 to u2 to dot say un. They are the set of vectors. Okay, this particular set gamma is called an orthonormal set, and orthonormal set, just a definition, orthonormal set, it's called a orthonormal set provided all these vectors, say I'm representing as this kt1, kt2 and so on, ktun. So if every kt of ui, if their norm, okay, if their norm is 1, so obviously you can compare it with a quantum state. Okay? And also if for any two such vectors ui and uj, if their inner product is basically delta function lambda ij, that means it is equals to actually 1 if I equals to j. Okay, otherwise it is actually 0, means their dot product is 0 for any two different state. If I not equals to j, then all such the set of all such vectors is called the orthonormal set. Okay. So this is the set orthonormal set. So we every orthonormal set is linearly independent. Some facts you know. So they are this orthonormal set, they are linearly independent. Linearly independent. Independent, and every orthonormal set of n vectors form an n-dimensional space, so which is an orthonormal basis for the vector space V. Okay, just to keep a note, sometimes we'll cover the probability theory, but just to keep a note for this particular part, if you have two random variables x and y, say some random vectors x and y, they may be some random vectors. Okay, so if you take the inner product of them, okay, so you will get basically the expectation of that product x into y. So this particular part will come at some time for the random variables. Okay, for the random variables, this is the inner product of two random vectors is the expectation of that product. Okay. So this is the conclusion. In summary, we have what we have covered. Basically, we have covered the matrix norm, different kind of matrix norm, Frobenius norm, and all. So we have discussed the inner product space. Okay, inner product space, and also the orthogonal set of vectors, or the orthogonal set Okay, so in this particular lecture, next we'll cover very interesting and very important one, which is called the theory of special matrices. Okay, so this is the topic for next class, the special matrices. So where all such concept of norms will appear. So and we'll come across the quantum evolution part. So special matrices will cover the unitary matrix, the rotation matrix, the reflection matrix, and the projection matrices and their properties, their eigenvalues, their determinant. And those things will be very frequent to the quantum literature, because the quantum evolution summum will be a unitary operator to preserve the reversibility operations. So thank you for joining this class, and see you in the next class.